This is a talk about grid shell design using Rankine's 3D graphic statics. I'll keep it simple. I'm Allan McRobie and I work with these good people. A common approach to grid shells projects everything to a horizontal plane and it does 2D graphic statics there. Instead, we'll take everything up a dimension and use 3D Rankine reciprocals. There are precedents in my own work and in that of Masoud Akbarzadeh and others. Many of those developments are more general than we need here, where we focus on vertically loaded grid shells. Perhaps later more general loads, moments and the like may be added back. Maxwell represents forces by the lengths of lines, whereas Rankine represents forces by polygonal areas, and these are very different worldviews. Here, a roof node carries a vertical load and the three bars that meet there are projected to a horizontal plane. Here we draw the Maxwell force polygon in red. That red line is perpendicular to that blue bar, and its length gives the horizontal component of the bar force. Vertical components, such as the applied roof loads, are invisible in the Maxwell force diagram. To assimilate the Maxwell 2D and 3D Rankine descriptions, place a pole at a depth delta below the Maxwell force diagram, and to keep things simple, let delta equal 2. Now draw lines connecting the pole to all the nodes of the force diagram. This is called coning, and under every polygon of the Maxwell force diagram it creates a Rankine polyhedron shaped like an inverted pyramid. This sloping face of the tetrahedron is perpendicular to the sloping roof bar, and its area represents the total bar force, with its two projections giving the horizontal and the vertical components. The area of the horizontal projection is half the width times the height, and since the height equals 2, the area equals the width. Ta-da, we've done it. Area equals length, so Maxwell and Rankine agree. Also, we now get a geometric description of vertical equilibrium. The vertical component of the bar force in bar 1 equals the sum of the applied load and the vertical components in the other two bars. The area of that red triangle is the applied vertical force, so it is no longer invisible. That triangle is from Maxwell's original force diagram. Areas of Maxwell force polygons now correspond to vertical nodal loads. The pieces fit together nicely to give a coherent geometric picture of form and forces. To use this in design, we start by choosing a 2D force diagram and then create a corresponding roof. Here we pick a Maxwell force diagram where the top layer is this tessellation of 9 triangles and the lower layer has this central node here connected to all the perimeter nodes. The perimeter edges are the same in each layer. Now, to generate the corresponding form diagram, define a polyhedral area stress function over the force diagram. I've shown that here. It has a red surface over the triangular tessellations and a green surface over the layer with the central node. And these red and green functions meet along the common outer boundary. As usual, the gradients of this polyhedral area stress function define the nodal locations of the 2D form diagram. So, we started with the forces and we generated the dual form diagram shown here with this central inner hexagon. Now go to 3D. Add the pole below and comb both layers to generate a set of Rankine tetrahedra. We also need one extra polyhedron to complete the full polytope. It has 0 thickness and it has 18 faces, 9 red and 9 green, and it joins the two original layers. Now define a piecewise linear Rankine stress function over these polyhedra by choosing values at every node. These can be the original area values. The only value not so defined is at the pole below, and for now let's set that to 0. Now take the gradient of the Rankine stress function across each tetrahedron, and analogous to the area case, each such gradient defines the coordinates of a node in the 3D form diagram. There is our 3D form diagram, our roof. I've thickened the bars using Rankine-Minkowski to make it easier to visualise. Here it is in more detail. And it is not just a roof form, it is a loaded funicular roof which can carry the applied loads by purely axial action. The applied loads are the areas of the red triangles in the original tessellation, and the green triangles correspond to the support reactions. An important feature of this procedure is that all roof panels are necessarily plane faced, and this is a direct consequence of the Rankine construction. So there we are, we have a loaded funicular roof with flat face panels. Once coded into MATLAB, it is easy to generate other examples. Here the force diagram is a grid of quads, and these area stress functions lead to this simple Rankine roof. There are various design freedoms in this process: the geometry of the initial force diagram, the area stress function, the locations of pole and central nodes, all can be readily varied to generate new roof morphologies, all with flat panels, all funicular for the load case defined by the initial force diagram. Again, the equilibrium forces and reactions come for free but are not shown. It is an interesting environment for generating forms. Here are some other variations by Giancarlo using rhino and grasshopper. The paper contains many other examples. Here a hyperbolic area over a triangular mesh led directly to a roof with flat concave hexagons. Here another triangular mesh leads to a roof with quad faces. The quads are actually hexagons with coincident nodes, so maybe this is a convenient way to generate quad roofs. Here Giancarlo is using standard finite element software to check that loads are indeed carried by purely axial action. Much can be readily generalised. Indeed, Masood's work has already done this, as has my own work generalising Rankine to handle axial shear, bending and torsion in fully general 3D frames. People sometimes find that rather complicated, so here I hope I have shown just how much can be accomplished while keeping things simple. No partial differential equations, no matrices, just geometry. Thank you for listening.